Hello everyone. After studying the basic principles and properties of quantum mechanics, let us move on to the next concept where we are going to discuss about some simple application. So here we are going to discuss about the eigenvalues and eigenfunctions of particles in different conditions. So what actually is eigenvalue and eigenfunction, the properties of wave function, the basic postulates are covered till now. But now on we are going to take those information and build up our next theory where we are considering certain conditions over a particle and the corresponding eigenvalues and eigenfunctions will be calculated. Under this we are going to study the eigenvalues and eigenfunctions of a free particle. Next, for a particle in an infinite square well. Third one is for a simple harmonic oscillator, and fourth one it is for the barrier transmission. So all these four applications will be discussed in my coming classes. First, let us start with the first one, that is eigenvalues and eigenfunctions of a free particle. First, let us know what actually is free particle. Whenever we hear a word free particle, we just say that there is no obstruction for the movement of a particle, then it is said to be free. So mathematically, let us find out what all parameters are going to be constant or zero. So no obstruction means there is no force acting on it. So we can say that F, which is force, equal to 0 for a free particle. So after studying all the terms, let us define what actually you mean by a free particle. Then later we can move for the derivation of eigenvalue and eigenfunctions of free particle. From Newton's second law, we have F is equals to m into a formula, where m is the mass and a is acceleration. And for a free particle, F is equals to 0 means m into a is equals to 0. Mass of the particle or the system cannot be equal to 0. It means that acceleration has to be 0. And acceleration is 0 means velocity is constant, because acceleration is nothing but rate of change of velocity. So for a free particle we can say that force is 0 and velocity is constant because acceleration is 0. Next, another form of equation is that F is equals to dp by dt, where p is the momentum. And this is again from Newton's law, and if dp by dt is equals to 0, when you integrate we get momentum p is equals to constant. And classically we know that momentum is nothing but product of mass and velocity, due to which we can say that velocity is constant. So both are in agreement with each other. Then we have another form of definition for force, where we say that force is nothing but negative gradient of potential. And if it is equals to 0, we get V is equals to constant. So potential of that particle is constant. So by remembering all this mathematical outline, we can define a free particle. That is, if a particle or a system moves in a region of constant potential V, then the force F acting on it is 0. Then the particle or the system is said to be a free particle. So this is about free particle. Next, first let us find out the eigenfunctions of a free particle. For that we need to consider time dependent Schrodinger equation. In general we just say it as h psi is equals to E into psi, where h is the Hamiltonian operator, psi is the wave function or eigenfunction, and E is the energy eigenvalue. So in place of which we are having Hamiltonian operator as minus h cross square by 2m dou square by dou x square for one dimension plus V of x, that is a potential energy term, into psi of x comma t is equals to energy, that is IH cross by IH cross into dou by dou t of psi of x comma t. Here we have considered only one dimension, that is along x axis. And time dependent means, as already discussed, wave function depends on position as well as time. Then such relation is nothing but the time dependent Schrodinger equation. Let us call it as equation number 1. Then for a free particle, we have already seen that potential V of x is equals to 0. That is nothing but potential energy. If you substitute this in equation number 1, the second term will vanish and getting minus h cross square by 2m dou square xi by dou x square is equals to I h cross dou xi by dou t. Let us call it as equation number 2. We want to find out what actually is xi of x comma t, which is the eigenfunction for a free particle. And in order to solve it, we need to use the separation of variables method. That is, the wave function, which is depending on position as well as time, has to be separated into two terms. One is explaining about the position dependence and another one is only with respect to time. So that simplification becomes easier. That's why we can write xi of x comma t, which is a capital Xi, is equals to small xi of x into t of t. First, xi is depending on position and the second term t of t is nothing but time dependent term. Let us call it as equation number 3. In order to solve and find out the solution for equation number 2, let us substitute the value of xi of x comma t. In the LHS part, we are having dou square by dou x square, which means differentiation is with respect to position. That's why xi of x will be inside the differentiation part and t of t, which is time dependent term, will be acting as a constant. So I am taking it outside and writing it as minus h cross square by 2m t of t into dou square xi of x by dou x square. And this will be equal to I h cross dou by dou t of xi of x into t of t, when xi of x is independent of time, that has to be taken outside the differentiation. Again, we observe that LHS term is depending on time as well as position, so as that of RHS also. And for simplification, we need to separate the terms. That is, one term should be only depending on position and another term should be only depending on time. So separating it, for that we need to divide the equation by xi of x into t of t. When we do that, in the first term we cancel the time dependent term and in the RHS side the term which is depending on position xi of x will cancel out and we are remaining with equation number 4. So we observe here LHS part, which is minus h cross square by 2m dou square by dou x square. It is relating to the kinetic energy and RHS part is nothing but IH cross dou by dou t, so which is nothing but the total energy. And for a free particle, we have seen that potential energy is 0, which means the particle has only the kinetic energy as there is no bondage on it. So total energy is nothing but the kinetic energy. So the contribution for total energy will be only from the kinetic energy of the particle. So this will be equated to capital E, which is nothing but the total energy of a particle. Now we can observe that first term on the LHS is totally depending on position, which is xi of x and dou square by dou x square, whereas the second term on the RHS is only depending on time. So now we have separated both the variables and finally we can find out what is the solution for xi of x and t of t. For that, let us consider part by part. First, let us find out what is the solution for t of t. So we are considering second term and equating it to the last term, which is e. In order to get the solution for this equation, we need to integrate it. So rearranging e by IH cross will be equal to 1 by T of T into dou T of T by dou T. So when you integrate, the first part is something like the term is in the denominator and its derivative in its numerator. That's why this type of integral will be solved and the answer will be equal to ln of the term. So ln T of T will be equal to E by IH cross can be written as minus IE by H cross, because 1 by I is nothing but minus I. So that is remaining as a constant, and integration over dt we get T. So RHS term will be minus IET by H cross plus ln C, where ln C is nothing but the integration constant. So if you solve it, we can find out what actually is T of T. So ln T of T minus ln of C can be written as ln T of T by C, which will be equal to minus IET by H cross. And if you take ln on the right hand side, we get the term for T of T, which is a time dependent term of the wave function, equal to constant C into exponential of minus IET by H cross. Always we just define, or many a times we define energy with respect to omega, and we know that in quantum mechanics E is equals to H cross omega. So if you substitute it, H cross will get cancelled out and we are remaining with the solution for T of T, which is equals to C into exponential of minus I omega T, and this will be called as equation number 5. So one part of the eigenfunction is solved, the solution is found out. Now let us find out the solution for the second part, that is what actually is the solution for xi of x. For that we need to consider the first term equated to the total energy E, which is constant. Again we need to solve it, so we are rearranging and we get an equation dou square xi of x by dou x square is equals to minus 2m by h cross square into E into xi of x. So the RHS term is brought on LHS and we get this equation. We know that 2me is nothing but p square, because momentum p is equal to square root of 2me, which is a classical result. So we have substituted it, and quantum mechanically we can define momentum in terms of wave vector. So we say P is equals to h cross k. When you substitute P is equals to h cross square will get cancelled out, and finally we are remaining with k square. So this is a form of equation which is same as that for the simple harmonic motion. So as it is a second order differential equation, we will get two different solutions for xi of x. So solution will be xi plus of x is equals to a into exponential of ikx, and xi minus of x will be equal to b into exponential of minus ikx. Exponential of ikx is nothing but sin cos kx plus I sin kx. So this is the solution for this simple harmonic motion or second order differential equation, and this can be clubbed, that is we get the solution for xi of x as sum of the terms, which is a exponential of ikx plus b exponential of minus ikx. Let us call it as equation number 6. So when we club equation number 5 and equation number 6, we get the eigenfunction for a free particle, which is nothing but capital Xi of x comma t is equals to a into exponential of ikx plus b into exponential of minus ikx into the time dependent term, that is exponential of minus I omega t. Here we have not written about c as it is a constant, so it can be included or it can be omitted, because when you just multiply it with the other constant a and b, finally you are leading a new constant. Finally, it is a constant itself, but the main outcome or result will be from the exponential terms. So, we can write xi of x comma t in this form. Next, let us see what actually this result interprets. So xi of x, it has to be finite for all real positive values of k. That is the condition put over xi. And that's why energy, that is the total energy, is also going to be finite. And therefore, all real positive values of energy are nothing but the energy eigenvalues, because those are the only measurable quantities. And as there are different values of k, the corresponding energy values are also going to be there. That's why the energy is continuous but not quantized. That is the nature of energy eigenvalue. Then xi of x, if we observe, it is formed as a linear combination of two linearly independent functions. One is exponential of ikx and another one is exponential of minus ikx. If you just remove that a and b. But what actually these two terms mean? So if it is exponential of ikx, it means that the particle is moving from left to right side, that is in the positive x direction, and the corresponding momentum will be greater than 0, which will be equal to h cross k. And the other solution is exponential of minus ikx, means that the particle is moving from right to left side, that is in negative x direction, where the momentum will be less than 0, which is defined as minus h cross into k. So based on this, we just say that the system is doubly degenerate, or the wave function, it is doubly degenerate. What does it mean? That is, the energy is same, but for the same energy there are two different eigen states or two different eigen functions. This is the meaning of it. One is in positive x direction and another one is negative x direction. So here we need to understand that there is only one energy, but mathematically again we need to prove it whether it is true or no. So let us do it. Before that, the functions which are the constituents of e raised to ikx are nothing but sin kx and cos kx, and these represent the standing waves which are obtained by superposition of opposing wave motions. So this is about the significance. So finally you are getting a stationary wave, or the standing wave we can say. Now let us find out what is the energy eigenvalue corresponding to the eigenfunction xi of x comma t. For that, again we are considering the Schrodinger equation, which is nothing but, or even you can say it as an eigenvalue equation. H xi plus of x is equals to E xi plus of x. Even you can consider the solution xi minus of x. Finally you are going to lead with the same. Substituting the value of h and xi plus of x. One thing to remember is we are considering the free particle. That's why v of x will be 0. So h will be equal to minus h cross square by 2m dou square by dou x square. Substituting the value of xi plus of x, that is a into exponential of ikx. We need to take differentiation 2 times. So once when you differentiate, we get aik into exponential of ikx. Again differentiating, because it is dou square by dou x square, we get aik whole square into exponential of ikx. So I square is nothing but minus 1 a k square e raised to ikx, which is equals to e into a e raised to ikx. So here a into e raised to ikx will get cancelled out. Minus minus will become plus. So we are remaining with e is equals to h cross square k square divided by 2m. And this is the eigenvalue for a free particle. And this is very important relation which relates energy with the wave vector and shows the quadratic dependence of energy on wave vector. So any free particle which is moving in any material, even you can say for a conductor or a semiconductor, the energy will be defined with this equation itself, because the particle, it may be electron or a hole, they are moving, means they are acting as a free particle. So the energy will be equal to h cross square k square by 2m. This is about eigenvalue, and if you find out the same for xi minus of x, the answer will be E is equals to h cross square k square by 2m. You can just try it out. So what we observe here is, we are having two different solutions. One is xi plus of x, another one is xi minus of x, which represent two different states. And for those two, we are having the same energy. E is equals to h cross square k square by 2m. Means for one energy, we are having two different eigenfunction, which means that the state is doubly degenerate. So this is the significance of understanding the eigenvalue and eigenfunction of free particle. And based on the energy range, we can define different particles. That is, if energy eigenvalue is greater than 0, it means that the particle is fully free to move. That is, it is acting as a fully free particle. And let us say energy is equal to 0. Then the particle is just free, means it was bounded but now it is free to move. But it is not 100% free, so it is something like a boundary. If energy is less than 0, then the particle is a bounded particle, means it is not free to move. It is bounded to, if it is electron, it may be bounded to the nucleus or the atom. It is something like that. So based on this energy eigenvalue, we can define different types of particles also. So this is about the eigenvalues and eigenfunction of a free particle. So in my next class, we will be discussing about the eigenvalue and eigenfunction of a particle in infinite square well. This is for today's class. Thank you.